Let's understand what do we mean by schedule in transactions. The schedule in transaction means that when we have more than one transaction executing at the same time, okay. For example, here in the figure we see there are two transactions T1 and T2, and both of them are executing in the same time. And they have a specific order. They follow the order. For example, T1 executes reading on item A, writing on item A, reading on item B, writing on item B in some order. And then T2 does its work in some order. For example, reading, writing, reading, and writing. And it is reading B, it is reading writing B, and then it is reading item A and writing item A. So these transactions are supposed to do some work. The actions inside it are also following some finite order or a definite order or a chronological order. Then this set of transactions executing together with some specific order of their actions inside it is called as a schedule. For example, we have a set of two transactions here. Some particular operations are executed as shown. This is called as a schedule. Okay. Schedule in DBMS is divided into two types. One is called as a serial schedule. Okay. And another one is called as a non-serial schedule. We will see the examples of each after some time. The non-serial schedule is again of two types, serializable and non-serializable. Serializable schedules can be further divided into conflict serializable and view serializable. Non-serializable schedule can be divided into recoverable schedule or non-recoverable schedule. And recoverable schedule can be recovered by cascading it or cascadeless or script or strict schedule. We have discussed about the recoverability of transactions by using these three methods already in the previous transaction videos. Okay, so in this video we are going to understand what do we mean by serial schedule, non-serial schedule, serializable and non-serializable schedule, and specifically we are going to concentrate understanding conflict serializable and view serializable. Now, these terms are very important. We are going to use this term more often in our slides. This slide talks about a transaction schedule or a transaction history wherein you see T1 is executing all its transactions. After T1 completes its transaction, T2 is starting its work. This is a schedule A, and this schedule is called as a serial schedule. After completing T1, T2 starts. So, hence the schedule A is said to be serial. Okay. Now, this is an example of a serial schedule. We said this one right. Serial means one transaction is completing, then the other transaction starts. Okay. Now let us see what is transaction schedule. We talk about it. Okay. So okay, we can skip this. Here, let's see an example of a serial schedule and a non-serial schedule. Okay. If you see here, we have transaction A executing all of its operations. After it completes, T2 is starting. Now this T1 and T2 here makes schedule B, for example. Then the schedule B is said to be a serial schedule. Okay. Now let us see a schedule S of transaction T1 and T2. A schedule S or C S is just a name. Okay, here we have a transaction name C. So it's okay. This is transaction B we can consider. So any transaction schedule S having number of transactions inside it, T1, T2, and so on. Now we have to notice these words. It is an ordering of operations. It is an ordering of operations. Okay. of the transaction subject to the constraint that for each transaction T1 that participate in S, the operations of T1 in S must appear in the same order in which they occur in T1. Okay, so however, the note here that the operations from the other transaction Tj can be interleaved within the operations of Ti in S. For example, here we say T1 is interleaved, T2 is interleaved. It means that T1 is starting. Okay, before T1 completes, T2 is starting. Before T2 completes, T1 is again starting, which is interrupted by T2. Okay, and then which is interrupted by T1 back. So here, this is a way of TJ, like a second transaction, interleave within the operations of TI. So this is your T1, T2, T2 transactions are interleaved with the operations of T1. Okay, so this is possible. Okay, and what does we say here? Each transaction Ti participate in S. Okay, if this is your Ti and it is participating in S, then in S must appear in the same order. So the transaction, for example, T1 is saying that read A. Now, when this T1 participates in a schedule, it will read A as a first job. Okay, then this transaction is saying A is equal to A minus N. Now, the second operation after T1 participates in a schedule will be same. Okay, so it's something like you have an order of learning. For example, you want to uh, you have your own schedule, right? For example, you want to attend the classes in the college, you have your same schedule. You have your specific schedule given to you. The timetable is given to you. Okay, now when you implement this timetable with other students of the same class, your timetable is not changing, you're following the same timetable pattern. That is what we mean here. Okay, any transactions in Ti when it is participating in S will follow the same order as it was there in Ti. Okay, so if T2 want to participate in the schedule, then what is the first transaction of T2? It will be the same transaction of T2 in the schedule also. Okay, that's it. Now let us understand the serial and non-serial once again with an aid of a transaction S1 and S2. I will say that S2 is serial. S2 is serial schedule. I will say that S1 is non-serial schedule. What do we mean by this? It means that there are two transactions schedule 2, there are two transactions schedule 1. Now, in serial schedule, one transaction is executed completely before starting another transaction. So I will completely execute T1. After it finishes, then only T2 will start. So this is called a serial. It's like, the T1 completes first, then T2 starts, and T2 completes next. This is the example of serial. So it is like T1 is reading item A, writing item A, reading item B, writing item B. That's it. T2 will wait until T1 finishes, and then it will read A, write B, read B, write B, read item A, and write item A. So it's like, for example, you are waiting for your friend to complete her exam, and then you start writing your exam. This is a serial schedule. This is an example of a serial schedule. Okay. But in real life, the exams are not serial, they are interleaved. Not even interleaved, they are parallel. Okay. The opposite of serial is non serial schedule, wherein the operations from set of concurrent transactions means two transactions running at the same time interleave with each other. Here, the concurrent transactions are overlapping. For example, here, the transaction T1 starts, okay, and it reads item A, okay, and then it writes item A. Then T2 starts and it reads item B and then write item B. Then the transaction 5 is taken care by T1, reading the operation on item B, then items, writing the item B, then reading item A, then writing item A. So you see here, the first the first action inside, how many operations are we performing? 1, 2, 3, 4, 5, 6, 7, 8. So operations are listed here. The first operation is performed by T1. Second operation is performed by T1. Third operation is performed by T2. Fourth operation is performed by T4 and so on. So here T1 is working and then it is waiting. T2 is starting working. Then after T2 finish, T1 again is starting, and then after T1 finish, T2 is starting. So T2 is not waiting for T1 to complete before starting itself. It's starting in the, in the meantime. Now, we have discussed the serial schedule. We have discussed the non-serial schedule. Now, inside the non-serial schedule, we have something called as serializable. Okay, inside non-serial schedule, we have something called as serializable. Okay, which have two children called as conflict serializable and view serializable. Now, let us understand what is serializable. Hmm. Can you look at this figure? You're reading A again with another transaction. You're writing B, okay? And you are reading A, then you're writing B, and in the other transaction is only reading A. Now, here, if you change the order of, if you change the order of, for example, you make the read A transaction 1, then B, then read A, then read B. So you're completely doing T1 and then pushing this read A after you're done with the transaction 1. The result will not change because the second transaction is only reading A. The first transaction is also reading A. The first transaction is also reading A. The second transaction is also reading A. So when you're reading and you're not writing, the order doesn't matter, right? For example, I am reading the newspaper. You are also reading the newspaper. I read first, the data is not changed. You read first, the data is not changed. So it doesn't matter you read first or I read first, it is same. So such transactions wherein the order is changed also produces the same result of the database, and it is called as serializable schedule. Now let us understand it by its definition. A schedule S, okay, this is the schedule S, is serializable if it is equivalent to some serial schedule of some n transactions. So it means that it is equivalent to, S is equivalent to, executing it in some serial way. Then it is called as serializable schedule. Okay. Okay. Now, in more simple words, serializable. Yeah. Now you see, students here, the serializable is interleaved, but interleaving is not affecting our results. For example, here you make the value of A as, for example, here the A is 10. You read A as 10. You read A as 10 here. Then you write the value of B 5. Then you read A. A is 10 again. Okay. And then you write the value of 5. For example, 7 new value. Okay. And then you read A, it is 10. Okay. So if this schedule is giving you 10, value of A as 10 and value of A as 10. Okay. And if this is your schedule. Okay. Now let us talk about another schedule, S1. Okay. Now, for example, here I do the write first and then I push this read here. Again, it will be 10 only, right? If I push all these reading to the end, It will be 10 only. So changing the order of transactions or changing the order of operations inside the transactions of two different transactions are still producing you the same result. Then it means, mm, although it is interleaved, although they are parallel, they are coming in between each other, still they are leaving the database in the consistent state. Then it is called as serializable. Okay, now let's see more an example of it. A serializable ensures that the final state of the database remains same with the results obtained from SQL execution of the same transaction, even though the transactions are running in the same time and their operations can be interleaved with each other. Then it is called as serializable. So it is interleaved, okay, plus serial. Okay, why are we saying interleave? Because they are coming in between each other, right? They are coming in between each other, but still they are producing the same result. There is no change in the value of A. Okay, so this is serializable. Now, what is the difference between serializable and serial? Serial is simple like this. Transactions complete, you complete one transaction, then only you start another transaction. Here you might change the value of A. For example, you're writing A. Okay, here you're writing A. This doesn't affect. We want the first transaction to complete first, then the second transaction will start. This is called as serial schedule. A schedule S is serial for every transaction T participating in the schedule. For all the operations of T are executed consecutively, here parallelly, here consecutively, here concurrently, here one after the other in the schedule. This is the difference between serial and serializable. Okay, now let's move further. Being serializable is not same as being serial. Yes, we agree to this. Are these two things same? No, they are not same. Okay. Do you see here the order how the transaction is written? Yeah. And here, how is it written? Yeah, they are both different. So serial is different, serializable is different. It means that serializable is not the same as being serial. Being serializable implies that the schedule is correct schedule because we are having the same value of the data item. Even if we, even if we run two transactions in an interleave way, it is same. It will leave the database in the consistent state. Why consistent state? We are saying, for example, here we saw that the value of A was 10 in the beginning and the transaction 2 also read it as 10 in the end. So the final state is consistent. Here the value of A is equal to 10. In the end also here the value of A is equal to 10. Okay, that is why the final state is same. When the final state of the database is same, it means it is consistent. Okay. The interleaving is appropriate and will result in the state as if the transactions were serially executed. Okay, so when you have a serializable schedule, even if they look interleaved, they are working like a serial way. Okay, that's why serializable. The interleaving is appropriate and will result in the state as if the transactions were serially executed, yet will achieve efficiency due to concurrent execution. Okay, so something like yeah, our college timetable is serializable. For example, we all work from 7:30 to 4 o'clock or 5:30. all of us, all the teachers and all the students and the college is working. But you see, we are working parallelly, but my timetable is not conflicting with your timetable. Okay. So when you are free and when I am free, I take your class. Okay. Otherwise, I'm busy doing my work. You are busy doing your work, and we are actually completing. Now let us learn about the places where there can be a conflict. If there is no conflict, then we are going to tell that case is result equivalent. For example, we have case 1, and in the case 1, we are testing two schedules, S1 and S2. S1 is running transaction 1, then transaction 2. S2 is running transaction 2, then it is running transaction 1. However, because they all are reading the value of data item A, the value of A did not change, and S1 and S2 produce the same value of A. Hence, it is said that S1 is equal to S2. There is no conflict. And also notice that whenever we have read and other transaction is also reading, no one is writing, then there is no conflict. We saw. Okay. Either T2 reads it first or T1 reads it first, the value of A is going to be 5. Similarly, if we have read and write, okay, if we have read and write on a different data item, for example, T1 is reading A as 5, T2 is writing B as 10, and they are doing the opposite job here. Then also, because both the transactions are working on different data item, there is no problem. You are writing in your book, I am writing in my book. We are not conflicting with each other. If you and me are writing in the same notebook, then there is a conflict. It is like, you are also working on the same mobile, I am also working on the same mobile, then there is a problem. If you have your own mobile, I have my own mobile, so it's like different data item. You write your things on your mobile, it is not going to conflict with me. So this is the case 1. This is called as result equivalent. Okay. Now let us see the case 2. Here we have read and we have write on the same data item. As I told you, if you have your mobile phone, okay, and I am writing in your mobile phone, so I will write a different value, you will write a different value, and our data item is having two different values when you are using mobile, when I am using mobile, then it is called as there is a conflict. Let us understand here what is happening. S1 is allowing T1 to read the A value as 5. Then it is allowing T2 to write the value. T2 wrote the value of A as 10. This schedule finished, wherein the resultant value of A is 10. S2 is writing a new value on A, okay, as 15. Then T2 is reading it as 15. The value of A in S1 was 10. The value after running S2 is 15. The results are not same. Hence, S1 is not equivalent to S2. There is a conflict. So are you understanding when the conflict comes? If we have the same data item and one of the transaction is reading, another one is writing. If there is a single write, at least or more than one write, there is a conflict always. Now, case 3. S1 is running T1 first, then T2. It is allowing T1 to make the value of A as 5. Write the value of A as 5. Then T2 reads A as 5. So what is the result? Here, after running the S1, value of A is 5. S2 is running T2 first. So it is reading the value as 5. Okay, then S2 is allowing T2 to make some changes. So it made the change as 10. So here if you run S1, the data item is going to be 5. If you run S2, then the data value is going to be 10. Hence, S1 and S2 are having conflict. Okay, so you notice here we have one write, there is a conflict. You have one write, first write followed by a read, we have a conflict. If we have both the writes, then also there is a conflict. For example, S1 is trying to write the value of data item as 2. S2 is, running the transaction to T2 first, and without reading, the transaction 2 is changing the value of A as 8. This is also called as blind write. It's like, T2 is trying to write on A without reading it first. Okay. So it's like, you are, working on the WhatsApp. You did not see the message of sender. You send the message without reading it. So there can be confusion. There can be, conflict. So this is called as blind right. And wherever there is a right and right, there is conflict. Okay, so these are the 4 places, out of which the first case doesn't have any conflict. All the other 3 places, wherever there is a single right or more than one right, there is always a conflict. Okay, now let's move further. Okay. Result equivalent. We know that if 2 schedules are running, in a different form, but they are producing the same final result of the database, then it is called as result equivalent. And we just discuss. Okay. Now we are trying to, let me tell. Okay. We are trying to transform S1 into S2. S1, as you see, it is non-serial. Part of T1 is running, then part of T2 is running. T1 run, then part of T2 is running. Then T1 is running again. And this time T2 stop, and then T2 is running. So now let's see. How can we convert this non-serial schedule to a serial schedule? Because now if you just notice, what is the job of transaction 2? The job of transaction 2 is to read the value of A, which is read by T1. Sorry, again, I will tell again. The job of, let us understand what is T2 doing. T2 is only working after T1 finished working. Okay, so it's like T1 is doing half the job, then keeping quiet. Then T2 is running. Then T1 is continuing, doing the rest of half job. Then T2 is running. So in this case, what are we doing? We are executing all T1 first, making T2 wait in this time, and then making T2 run all at once. Here we have all at once, and here we have all at once. T1 all at once, T2 all at once. Here, part of T1 is running, then T1 is keeping quiet, T2 works. The interesting thing here is the T1 is reading A, writing A. T2 is reading the value of A, which is written by T1. Then T2 makes some changes. Okay, then T1 read the value of B, another item now, and wrote a new value for B. After T1 wrote a new value, then only T2 is reading B and then writing B. So in all these cases, what we can do is we can shift this half job of T2 and let all the work of T1 finished first. We can just move the, sorry, I will repeat again. We will just move the half job of T1, okay, and make all the T1 run in once, and then move down the half job of T2 and run after T1 finishes. Because, every time if you see, okay, I will again quickly tell you one more easy thing to remember. T2 is reading A after T1 wrote. T2 is reading B after T1 wrote B. So what we are doing is we are just pushing up this half job of T1 and pulling down the job of T2 so that it looks like this. Hence, the non-serial is changed to serial now. Okay. Now let us understand what is conflict equivalent. Two schedules are said to be conflict equivalent if the order of any two conflicting operations is the same in both the schedules. You see here what is conflicting operation? We know wherever there is a write, there is conflict, right? So there is a write here, there is a write here, right? Now, what are we doing here? We are pushing the write, okay, this up, okay, and it is producing as the same thing. It is producing as the same thing, okay, just like the previous example. Then it is called as conflict equivalent also, okay, result equivalent, okay, and also conflict. Another way to test the conflict serializability is to make use of an algorithm. This algorithm creates a precedence graph, and the graph is checked for cycles. If there is no cycle, then only the schedule is considered to be serializable. If there is a cycle formed between the two nodes by the iterative or by the loop or the cycle, then it is not considered as a conflict serializable. Now let's see how it works. It looks at only item X, read operation on it and write operation on it on two different transactions. Remember that we have discussed the operations that can create conflicts will involve at least one write. For example, transaction T1 is performing a read operation followed by transaction T2 trying to write on the same data item. Then it is conflicting. Similarly, the write operation performed by the read operation from another transaction on the same data item, or both of the transactions T1 and T2 are trying to write on the same data item, then these are the three places where the conflict can happen. Based on this, based on this principle, the precedence graph is created. The precedence graph is nothing but a set of nodes and edges with directed arrows. An edge is created from the first transaction to the second transaction if and only if the first transaction is one of these conflicting transaction towards J. And similarly, an edge is drawn from transaction 2 to transaction 1 when it encounters one of the conflicting transactions given here. We will see this with an example now. Let's see how it works. We have a transaction, we have a scheduled transaction, schedule D, given as performing the read operation on X. So R1, and let's see how to make a table of the given schedule. In the question, in the final exam, you might be given a schedule like this with couple of operations, couple of read write operations on it. Now you need to simplify this by creating a transaction schedule table. How do we make it? Let's see. Now read this schedule. Here we have R1. It means this is the read operation performed by transaction 1. R2 means this is a read transaction performed on X by transaction 2. Here we have W1 means the write operation performed by transaction 1 on X. R1 again means this is the read operation performed on item Y by transaction 1. W2 means transaction 2 is writing on item X. And W1 of Y means transaction 1 is writing on item Y. Okay. With that said, let's make a table. Just simply write down how many transactions are involved in the schedule, 1 and 2. So we are writing T1 and T2. Now, pick up all the one transactions. Like here, R1, we wrote R of X here. Then we have R2, write down R2 here. R2, R of X. Then we have W1. So we write W of X here. Then R1 of Y, we write read on Y here. Then W2 means it is a write operation performed by the transaction 2. So it has to be written here. Okay. And then W1 on Y is write operation on Y. Okay. So this table is ready now. Now, how to create the precedence graph? Now, when we have the number of transactions, when we have number of transactions, those many number of edges are, those many number of nodes are created. For example, we have T1 and T2, so we created T1 circle and T2 node. Okay, now let us pick up the first transaction. You are the transaction 1 is reading on item X. Now we have to check for this conflicting operation. Read follow by write of another transaction. Let's see. Reading on X. Okay. Followed by writing. The opposite of read is write, right? So followed by writing of X from transaction 2. So how do we check? So we go to the first operation. It is not conflicting. This read is never conflicting with the read of another transaction. So we skip this. And then we come and check, find out here that there is a write operation performed on X by transaction T2. So this read on X with T1 is going to conflict with write of X from T2. Okay, so for A's, we just are making a row, an arrow here to just see that, this R of X is checked with this W of X from transaction T2. Okay, so how is it moving from T1 to T2? So what did we do? We draw a line from T1 to T2. Okay, now let's come and check with the other operation, the second operation from T1. The second transaction here, the second transaction here is writing on X. Now, writing on X followed by read or followed by write from the other transaction will create a conflict. So we are going to check now. We are going to check that after T1 is writing on item X, is T2 going to read it or write it? Why? Because we have W followed by R, W followed by W, that creates a conflict. So W of X, okay, is conflicting with X, but we already draw this. So we can skip. Okay, so we can skip. Now we have our read performed on Y. So read perform on Y. We don't have any read perform on Y. Then we have W of Y. Write perform. So doesn't matter if this read and this write is there. Now here, what's happening? You see, this WX, okay, is conflicting with this WX also, right? Because you see here, we have W followed by W, okay? So write on X, okay, is again creating a conflict with this write of X from T2. So this is from T2 to T1. Or we can also think it like this. For example, we consider this WX is, conflicting with this WX, and then we already draw the line, right? From T1 to T2. So stop doing that one and look forward. Check for our read on Y. We don't have read on Y, so there is no conflicting. Then we have write on Y. We don't have write of Y in the second transaction, so skip this one. Now come here on read of X. Read on X never creates a problem with another read of X, right? Then we come to the W of X. So here, this W of X, okay, is creating a problem with R of X. We wrote it already, but this W of X is creating a problem with W of X from T1 also. So from the transaction T2, we are making an arrow to T1. So here there is a cycle. Whenever there is a cycle, it means it is not conflict serializable. You see, the schedule is serializable if and only if the precedence has no cycle. But here we have a cycle, we have a loop. T1 is, creating a conflict for T2. T2 is creating a conflict for T1. And then we have the cycle here. So this is the easiest way how we create a precedence graph and find out that a given schedule is complex serializable or not. Another way is here itself, when the schedule is given, you can just find out that if it is serializable or not. How do we do that? Check this R1 of X with X written, because this R followed by W creates a problem. So we want to see X. Where is it written? X is written here, but because this is R1 and this is W1, it means the same transactions, right? Making changes on X is not a problem. So you skip this. Then you check for another X operation. So here there is a write operation on X data item, and here there is a read data operation on X data item conflicting. So these two operations are conflicting. Now read, transaction 2 is reading X. Now we have to see that is the transaction 1 writing on the same data item. We find it here that transaction T1 is writing on the same data item, which is X. So this is pointing here. So it's like we have two pointers, and when they are translated into the precedence graph, in this particular case, it is actually making a cycle. Hence, wherever we have a cycle, then that particular schedule is not considered as serializable. It's conflict serializable schedule. Now, another topic, which is called as view serializability. View serializability have three conditions. Okay, let's see what are the three conditions. These three conditions, okay? That, I'm just giving you hints to remember. The first condition says that two transactions are view serializable with each other when they have the same operations. The first condition is both of these schedules should have the same operation. The second condition is that their last operation must be right. Okay, I will explain you this with example. The third condition is that there should be a read operation followed by write operation in both of them. How is that possible? Like this. Okay, there will be two schedules given to you. This is schedule 1, this is schedule 2. The condition 1 says that the transaction 1 in both the schedules should be initially read. Here T1 is reading, here also T1 is reading. So the first condition is met. The second condition is that the last operation in both the transactions should be right. So here the last operation is writing on A, transaction 3. Here also writing A by transaction 3. So final write. Here let us check if the final write is there. Transaction T2 is writing last operation, first and last operation by transaction 2. Second transaction is writing. So it is following the first condition and the second condition. The last condition says that the read operation on first schedule should be followed by the write in the same schedule. So here we have T1 reading, T2 writing. In the second schedule, also the same thing. T1 reading, T2 writing. If these three conditions are met together, then the transactions in the schedules, the two given schedules are said to be view equivalent with each other. Now, what is view serializability? Why do we need to check these three conditions even? A schedule is view serializable if it is view equivalent. Okay, to a serial schedule. If a transaction is conflict equivalent, then it is view equivalent also. Okay, let's see more things about the one more example of view serializability. Here we have a transaction. Now we want to apply those three conditions what we have checked. This is transaction, this is schedule 1, this is schedule 2. Initial read of transaction 1, here also T1 is reading. The second condition is the final write. Here T3 is writing, here also T3 is writing. So the first is checked, the final write is also checked. The last condition is that when there should be a read operation followed by a write operation. Read operation followed by write in schedule 1, T1 is reading, T2 is writing. T1 is reading, T2 is writing. So it means that these particular schedule with the arrangement of T1 executing first, then T2, then T3 is view serializable. Practically, we need to come up with some methods or protocols to ensure serializability. It is not possible to determine when a schedule begins and when it ends. Hence, we need to reduce the problem of checking the whole schedule to checking only committed projects of the schedule. All the transactions and the schedules which are not committed, we don't want to check them at all. This is the current approach used in most DBMS. They make use of locks with two phases, two-phase locking. And then we discuss this two-phase locking in concurrency control mechanism. This is called as 2PL. Other types of equivalence of schedule includes a semantic constraint. Schedules that are otherwise not conflict serializable may work correctly or may not work correctly. We may check this by using commutative operation of addition and subtraction, which can be done in any order. Certain non-serializable transactions may work correctly, but we are not sure about it. Now we are going to talk about how to identify recoverable schedules. We already discussed that there are three types of recoverable schedules: cascading, cascadeless, and strict. Cascading is if a transaction T1 reads a data item previously written by another transaction T2, then T2 must have committed before T1 started. Then only the transaction can be recovered. Otherwise, the transaction cannot be recovered. A schedule S is recoverable if no transaction T in S commits until all transactions in T dash that have an item that T reads have committed. So no transaction needs to be rolled back. We will understand these two things with example, then you will understand it better. Here is an example. We have schedule 1 and schedule 2. Schedule 1 have three transactions: 1, 2, 3. T1, T2, T3. Okay. T1 is trying to read item X and make changes into item X. So R of X and write operation on X. Based on what T1 have written or T1 has written in X, T2 is reading it and adding or changing some value of X by writing it. Based on what T2 wrote, T3 read the value and changed the value. Now, in case if this aborts, if the first transaction aborts, T2 will also abort, T3 will also abort. So, abort of transaction T1 will lead to no value of x for T2. The no value of x for T2 will lead to no value of x for T3 because 3 was dependent on what T2 wrote. T2 was dependent on what T1 wrote for x. So if T1 is lost, T2 becomes empty, or the data value here in the data item x becomes empty. So T1 loses, T2 is also lost, then T3 is also lost. So we have series of aborts. Okay. Now, how to handle this? This is called as cascading abort. Now we will see how does the cascade less schedule works. The how to manage this. After T1, read the value of x and write the value of x. The same time we want to commit this. Only after committing, then we will allow the T2 to read the value of x and make changes on x. After making changes on x, then T2 commits, then only T3 can depend on T1 and take the new value of x and do whatever the T3 wants and then commit. So here we says that only after committing the other transaction can read. Now you will understand. A schedule is recoverable if no transaction T in S commits until all transactions in T dash have already committed. So this cannot commit until all these things are committed, and this cannot perform, any operation unless it takes the committed value from the previous one. Okay, cascade less schedule. We just understood the same thing. Uh, we talk about cascading aborts, which is nothing but a rollback. If the first transaction rolls back, the second transaction will also roll back, third will also roll back, fourth will also roll back, and all will roll back. Okay, so this is the cascading rollbacks or cascading aborts. Both are same. Strict schedules. Make sure that a schedule is a schedule in which a transaction can neither be read, even we are not allowing to read, or write an item X until the last transaction that performed or that wrote some value for X has committed. So I will not let any other transaction to use X for reading or for writing unless I have saved the changes of X. Are you getting the point? So this is called as strict schedules. Now, let us see why we were doing all these things. Schedules must be either conflict serializable or view serializable and recoverable for making the database consistent and preferably cascadeless. A policy in which only one transaction can execute at a time will generate. Excuse me, just give me a moment. The Zoom is just flashing on me. Okay. A policy in which only one transaction can execute at a time will generate serial executions, your serial schedules. But doing so will make sure that your database is always consistent. However, the degree of concurrency becomes poor, the system can go slower. Concurrency control schemes should be used and they should take care about the overhead. All these things we have covered in concurrency control mechanism. Some schemes allow only conflict serializable. Okay, so I want you to show this point. Some schemes allow conflict serializable schedules to be generated, while others allow view serializable schedules that are not conflict serializable schedules. We completed this one. Okay, now this. Transaction definition in SQL. DML language must include construct for specifying the set of transactions. This thing is covered in lab 9. Yeah, I believe lab 9, yes, for the transactions. In SQL, a transaction begins indirectly, implicitly. The transaction in SQL will always end with commit, okay, if everything goes well, if all the actions are performed correctly, or it will roll back. There are 4 levels of consistency specified in SQL 92. One is called as serializable, which is default. Repeatable read, read committed, and read uncommitted. Now we will see what are they. Read, dirty read. Dirty read is like reading a value that has been written by a transaction which failed. For example, you're trying to read A from T1 and the T1 failed, it did not commit. And in the dirty read, you took the value from T1 and it made a change on it, you wrote upon it, you perform a write operation on it, and then you commit it. So this is called as a dirty read. Okay, it's like you are depending on some information and you are adding your own information on it, but the information what you took never existed or it failed. So this is called as a dirty read. It's as in the simple words, it's just saying that trying to read the item A, which was written by transaction T1 and it did not save, and then before saving, you read it and T1 failed. Non-repeatable read, allowing another transaction to write a new value between the multiple reads of a transaction. For example, you have a transaction T1, it read the item stock as 10. Then it is doing some work. Okay, while it is doing some work, the transaction 2 came and added, updated the item stock to be 5. After you finish your work and you are going back to this, same data item, now you see another value, new value. This is called as non-repeatable read. Phantom problem is like transaction T1 is reading, okay, and while it is doing some another work, transaction T2, while still it is doing the same work or while it is busy, the transaction T2 inserted some new lines or some new data items. Then it committed also. Then the transaction 1 is now reading the data item with another value and then it commits. Okay, so this is called as phantom rows. The rows that have been inserted by another transaction. Here the count was different and now the count is different because there is new insert. It's like, for example, before writing the final exam, we calculate the students with more than 25% of absentees. So now think that, the Miss Fatma Farhan or someone, is trying to calculate the number of students. So she said that from section 61, 5 students are not eligible to write the exam. Okay. Meanwhile, here, the course teacher now knows that only 5 students are not eligible for writing the final exam. But when the course teacher is busy taking the exam, Miss Fatma Farhan added some more students to this not eligible criteria. So now, for example, she added 2 more. Earlier it was 5, now it is plus 2, 7. So these 2 rows are called as phantom rows. The transaction in SQL is given with this sample. So we have um, this is a sample transaction support given in SQL 2. Possible violation of serializability and type of violation is given here. Isolation level 1 is saying that allowing read uncommitted. So the dirty read is there if you set the transaction level as read uncommitted. Non-repeatable read is also there. Phantom read is also there when the transaction level is set as uncommitted. When the transaction level is set as read committed, you don't have dirty read, but still you have non-repeatable read and phantom prop. Repeatable read means there is no dirty read problem, no repeatable read, but still we have phantom problem. When you say serializable, when you set the transaction level as serializable, then we do not have read, dirty read, we do not have non-repeatable read and no phantom problem. Summary: in this series of transaction videos sessions, we have covered transaction and system concept, desirable properties of the transaction, characteristic schedules based on recoverability, characteristic schedules based on serializability, and support of transaction in SQL. With this, we are done with the transactions.